Composition of compounds. So we've been talking about chemical formulas. There's a lot of information in chemical formulas. When we combine the formula with molar masses, then that gives us relative quantities of each element in the compound. One way to express that is called the mass percent composition, sometimes it's called the mass percent of an element in a compound. So this is a general statement of what percent means. Percent is the part you're interested in, so here it would be the mass of the individual element, divided by the whole thing, would be the mass of the whole compound, and then multiply by 100 to make it a percentage. So to find the mass percent of an element, you can start with two different things. You can start with the formula of the compound. And then what you're going to do is you're going to find the mass of X in 1 mole of that compound, and you're going to divide that by the mass of 1 mole of the whole compound times 100. If you're doing an experiment, you may have actual data, the mass of this element and the mass of the compound, and so you take the mass of the element and you divide by the mass of the compound times 100. If you calculate the percentages of all the elements in a compound and add them up, you might not get exactly 100 because of rounding issues, but it should be super close. Okay, acetic acid is the active ingredient in vinegar. Calculate the mass percent composition of oxygen in acetic acid. Acetic acid is an oxyacid, there's the oxygen, and it comes from the polyatomic ion C2H3O2 minus, which has the name acetate. So you change the 8 to ic, and you get acetic acid. So this is one that students often don't recognize. So how do we calculate the mass percent composition? They're not telling us how big the sample size is, and they don't need to, because the percent doesn't change with the sample size. So we have to pick a sample size. So we might as well make it easy on ourselves, and we're going to choose 1 mole, because it's going to be easy. So we're going to find the mass of 1 mole of acetic acid. Well, that's the molar mass, right? So there's 1 hydrogen here and 3 over there. You can put those together and say, well, there's 4 of them. Or you can put them in separately. If that makes more sense to you, you'll get the same answer. I'm going to do them separately. So there's a hydrogen at the beginning, and then there's 2 carbons, and then there's 3 hydrogens, and then there's 2 oxygens. .052. That's the mass in grams of 1 mole of the compound. So we're looking for the percent of oxygen. So we need to know grams of oxygen divided by the grams of C2H3O2 times 100. This is the mass of 1 mole of the compound. So that goes in the denominator. The mass of oxygen in that 1 mole is actually hiding in the work that we did here. Right there. There's 2 oxygens, 2 moles of oxygen in every mole of this. So we'll take that out and put that up here. 2 times 16 grams. Or you could multiply it out and write 32, doesn't matter. So by mass, it's 53.29% oxygen. Questions? Mass percent can be used as a conversion factor. Sometimes there'll be a problem where they tell you what the mass percent is, and you can use that to do a calculation. Here we're going to take advantage of thinking about percent in a slightly different way, saying that percent means per 100. It is the part over the whole times 100. It can also be thought of as per 100. So if this is 69.58% chlorine by mass, then it's 69.58 grams of chlorine per 100 grams of the whole thing. And that can be used to convert between mass of the compound and mass of the element in the compound. What mass in grams of iron 3 oxide contains 58.7 grams of iron. Iron 3 oxide is 69.94% iron by mass. Again, let's see if dimensional analysis will work. So I've got a couple of numbers there. The question is what mass in grams of the compound. So I'm going to take my numbers and I'm going to start writing them down with their units. So I've got 58.7 grams of iron. And then I've got this percentage. That much percent of iron. When I write it like that, it doesn't look very helpful. That means there are 69.94 grams of iron per 100 grams of the compound. And we're short on time, so I'm not going to review how to write that formula, but there it is. We're trying to find grams of the compound. Which one of these are we going to start with? We're going to start with the one that can't be a conversion factor. Now, this has this per that. That's a conversion factor. Grams of iron is just a mass of iron. You can't really do much with that. So this is what we're going to start with. And then we're going to see, can we go from grams of iron to grams of Fe2O3? Well, this actually gives us that direct relationship, right? So I wrote these way far apart, but it's just a single step, actually. So 58.7 grams of iron. I'm just going to have one fraction here. Going grams of iron to grams of Fe2O3. When you have more than one substance in your problem, you need to specify grams of what. Otherwise, it gets really confusing and you're probably going to get the wrong answer. So I want to put grams of iron down here, so those are going to cancel out. I put all the units in. And then I'm going to look for numbers. So in this percentage, the 69 is with iron. So down here, I'm going to write the 69 with iron. Well, it helps to write the same number. And it was 100 grams of Fe2O3. The 100 here is an integer number that's part of an equation, so that's exact. So I've got 58.7 times 100 divided by 69.94. 83.929. The percentage I was given had 4 sig figs. My starting number had 3. So I'm going to end up with 3 and say 83.9 grams of Fe2O3. Some people have a really great grasp of percentages, and so you can just kind of look at this and say, well, yeah, I need to divide by the percentage. Other people, not so much, right? So if percentages are kind of confusing at times, they're confusing at times to me. I really like to write it down this way because then it makes a lot more sense to me. So not the only way you can solve this problem, but that's the way I'm showing you. Any questions? So the percent composition can be really useful. But there's a lot of information also in the chemical formula. The chemical formula gives us relationships between numbers of atoms and molecules. So if we look at this formula, Cl2, Cl4, F2, there's a bunch of different conversion factors we could make from that. One of them is that there are 2 moles of carbon for 1 mole of compound. In this formula, there are 2 carbons in this formula unit or molecule. So if I have a mole of it, then I've got 2 moles of carbon to 1 mole of the compound. I could look at the chlorine instead. Well, there's 4 chlorines for every molecule. So 4 moles of chlorine to 1 mole of compound. Okay? This is important. Chemical formulas give us relationships between amounts in moles, not masses and grams. Sometimes it would make the calculations easier if it was the other way, but it isn't, so there it is. Determine the mass of oxygen in a 7.2 gram sample of Al2SO4 SO43. Highlight the number. That many grams. It's the only number. We're asking for mass of oxygen. Let's try dimensional analysis. 7.2 grams of that compound. And I'm trying to find grams of oxygen. If we knew the percent oxygen in the compound, we could use that and do this in one step. And with the formula, you could calculate the mass percent of oxygen and then do it in one step. It's not actually any shorter than doing it the way I'm going to show you. So the conversion factors we get from the formula involve moles of things, right? We can look at this formula, and in one of these formula units, how many oxygens are there? 12. So there are 12 moles of oxygen per 1 mole of the compound. That's a conversion factor that is inside of that formula. It's just kind of hiding. We could also look at how many moles of aluminum to how many moles of compound. We could look at how many moles of aluminum to how many moles of oxygen. There's all kinds of different things we could do. But this is what's going to be useful to us. So this relates moles, and so we have grams at the end, but we're going to have moles in the middle. We can convert moles of that grams of the compound to moles of the compound. You're going to have to calculate the molar mass. And then we can convert moles of the compound to moles of oxygen using this conversion factor that we find hiding in the formula. And then we can convert moles of oxygen to grams of oxygen using the molar mass of oxygen. This is the hard part, figuring out how we're going to do it. Now we have a path, we have a map for ourselves, we just need to follow the map, right? Think about Dora. Dora, Dora, Dora the Explorer. She's super cool, Explorer Dora. 7.2 grams of aluminum sulfate. I've got three arrows. So I'm going to have 3 conversion factors. And I'm going from grams of that compound to moles of the compound. And yeah, it can be a little tedious and take some space to write all those things out. Just suck it up. Moles of oxygen to grams of oxygen. Then I'm going to put the units in the denominators so that everything cancels out the way I need it to. So those are going to cancel. And these guys are going to cancel. And those guys are going to cancel. We've learned one technique. See how you can string the units together so that you know a relationship for each of these. And we can use this technique to solve so many different problems. Relationship between grams and moles for the compound. Molar mass, we had to calculate it. We do a lot of calculating molar masses. So 2 times the mass of aluminum. And how many sulfurs are there? There's 3, right? Because there's SO4 and there's 3 of those. So 3 sulfurs, whoops. And 12 oxygens. to 46.17. One mole of aluminum sulfate, 246.17 grams. How many moles of oxygen in a mole of aluminum sulfate? 12. We get this from the formula. 12 moles of oxygen to 1 of those. And then the molar mass of oxygen, well, thank goodness, this is at least a little simpler. We can just look it up. We don't actually have to calculate it. 7.2 divided by 246.17 times 12 times 16. Starting number had 2 sig figs, so my answer is going to have 2 sig figs. 5.6 grams of oxygen. Did I do something wrong?
I think the molar mass is like 342.
342?
Yeah,
Could
like
be.
150 B.
Yes it is. I could go back and figure out what I did, but it's not worth the time. So my equation was set up correctly and miscommunicated with my calculator. Thank you for pointing that out. So I'll go back and change this. 4.04. That sounds more familiar. I did this problem yesterday, last night. Questions?